So good afternoon and welcome back. I hope you can hear me properly. Just a second. All right. So today we're going to continue where we left off in the last class. In the last class, we talked about the stability of linear time invariant systems. So we started with a small discussion on, brief discussion on asymptotic stability. And there we talked about how a system as a whole always cannot be described for stability. We cannot always describe the stability of a system as a whole. Sometimes we need to describe the stability of different configurations of the system. That is where asymptotic stability comes into action. And then we talked about Bibo stability. So Bibo stability is a very generic idea, and the idea is that if I have a system which produces a bounded output for every possible bounded input, then we call that system bounded input, bounded output stable, Bibo stable. Okay, and from there on, we actually derived a condition for linear time invariant systems to be Bibo stable. We derived that the necessary and the sufficient condition for Bibo stability of linear time invariant systems is the absolute integrability of the impulse response. So if the impulse response of a system is absolutely integrable, then the system is Bibo stable, and vice versa. So if the system is Bibo stable, then definitely the impulse response has to be absolutely integrable. That's what the necessary and sufficient condition actually means. Today, on that day also, we actually solved a few problems where we had the transfer functions, and from that we calculated the impulse response by doing an inverse Laplace transform, and from that we tried to figure out whether the impulse response functions or signals were absolutely integrable. If they were absolutely integrable, we said that yes, the system is stable, and if they were not absolutely integrable, then we said yes, the system is unstable. So that is the discussion we had yesterday. Okay, so today we're going to continue discussion, and we are going to simplify the understanding a bit more. Okay, and we're going to figure out a way of understanding the stability without actually doing the inverse Laplace transform. Sometimes what happens is that calculating the inverse Laplace transform to obtain the impulse response might become very difficult. And even if we can calculate the impulse response, it might be very difficult to see at a glance whether or not the impulse response is absolutely integrable, whether or not you can do an absolute integral on that and get a finite value out of that. So based on that understanding, we are going to now improve our method and figure out a way in which we can make the same conclusion, or rather draw the same inference about a system regarding stability, whether or not a system is bounded input, bounded output stable. Okay, we can actually draw the same conclusion, but not by doing the inverse Laplace transform and checking the absolute integrability. Okay, to do that, let's now talk about transfer functions in general. Okay, so we know that transfer functions in general are the Laplace transforms of the impulse response, but also they are defined as the Laplace transform of the output, the ratio of the Laplace transform of the output to that of the input for any linear time invariant system with zero initial conditions. So let me write down all those. So we are saying that we have a system, okay, it's a linear time invariant system, and its impulse response is gt. So the Laplace transform of the impulse response is gs, and the input that I have applied to it is xt. So the Laplace transform of the input is xs, the output and the Laplace transform of ys. Okay. Then we can say that the output is equal to the Laplace transform of the output is equal to the product of the Laplace transform of the impulse response and the input. So this GS, which is the Laplace transform of the impulse response, this is known as the transfer function. So let me just write it down. All right. So there is just one condition, that there are no initial conditions. So under zero initial conditions, physically, which means whatever energy storing components I have in it, they are not storing any energy before we actually start the system. Okay, so if I have capacitors, they are not storing any charge. If I have inductors, they are not storing any magnetic field. If I have springs, they are not initially stretched or contracted. If there are dampers, they are not initially at motion, such and such. Okay, things are not storing any energy. Okay, things that can store any energy are not doing so. Okay, all right. So under zero initial conditions, we have this kind of understanding here. All right, so that's the definition of the transfer function. All right. So as I was saying, that this ys and xs, they are polynomials because it actually comes from a differential equation, right? It actually comes from a differential equation. So essentially, the input-output relationship often looks like a differential equation in general for linear time invariant systems. Okay, for continuous time, let me write down. For continuous time linear time invariant systems, usually this is what the differential equation looks like. So this is the general form. Again, this is the general form we discussed earlier. So nth order derivative essentially. So we have multiple derivatives here, and these coefficients a1, a2, a3 up to an, these are constant coefficients. Then only the system is linear and time invariant. Okay. It's a general form, by the way. Anybody, if you have any question, feel free to ask. That's a general form describing okay, so you didn't miss much of anything, because something that we have discussed so far are the things that we already discussed in earlier classes, right? So this is the general form of the differential equation representing any continuous time linear time invariant system. All right, and also we mentioned that for the sake of causality and also sake of rationality, the order of derivative for x, the input, is less than or at most equal to possibly the order of derivative in for the output. So essentially, for rationality, we're going to explain this term later on. Okay, just for right now, just assume for rationality. For rationality, n must be greater than or equal to m. So n can at least be, so rather I should say m must be smaller than n, or it could at most be equal to n. Okay, so just keep this condition in mind. We are going to explain that in the proper context later on. Okay, so we could apply the Laplace transform and assume zero initial conditions. So applying Laplace transform, assuming zero initial conditions, you know what, let me just write the full form of LT. So applying Laplace transform, assuming zero initial conditions. So if I do that, of course, we know that if the Laplace transform of xt is xs, then the Laplace transform of the first derivative of xt is sxs minus some initial condition terms, but we are assuming zero initial conditions, so not a problem. So we eventually get something like this: an x to the power n ys plus a n minus 1 x to the power n minus 1 ys, and so on, a 1 s ys plus a 0 ys, and on the right hand side we similarly have bm s to the power m xs plus bm minus 1 x to the power m minus 1 xs, and so on, b1 s xs plus b0 xs, right? So that is something we usually write. Let me just increase the number. Right. Alright, so we have a formation like that, and of course with that understanding we can always express the ratio of the Laplace transform of the output to that of the input very easily. That's going to be an s to the power n plus a n minus 1 s to the power n minus 1 plus, and so on, up to a1s plus a0. So that's an nth order polynomial. Okay, and here we have bm s to the power m plus bm minus 1 s to the power n m minus 1, and so on, up to b1s plus b0. But again, keep in mind that all this a and b are constants, okay, for the sake of linearity and time invariance. All right, so that is the definition of the transfer function. In fact, this is the Laplace transform of the impulse response. So these are things we already have established previously, and we know these things quite well. Okay. Now again, we can actually do the inverse Laplace transform on this, and we can talk about the stability of the system. But I told you that we don't need to, because we are going to derive a technique with which we won't need to actually derive the impulse response out of this, and still we would be able to talk about the stability exactly the same way. Okay, so if a system is unstable, we can say the system is unstable. If a system is stable, we can say the system is stable. And then if the system is stable, later on we would learn techniques that would tell us, or rather that would allow us to quantify stability. Okay, so if I take two systems that are both stable, okay, we would be able to quantify how stable each one of them are. Okay, each one of them is. So the stability can also be quantified. So far what we are going to learn right now is a qualitative knowledge. So by doing some calculation, you will be able to say whether or not a system is stable. Okay, this is called the concept of absolute stability. So the answer is in absolute terms. It's a binary answer. The answer is so you would ask the question whether or not a system is stable. Is the system stable? The answer would be yes or no. So that kind of concept is known as absolute stability. And later on, we are going to actually use some quantifiers. We are going to figure out some quantifiers that we are going to use to compare two stable systems compared to unstable systems. So for example, I have two stable systems. Both of them are absolutely stable. Okay, they are both stable, but one of them can be more stable than the other. Okay, and that's true in real life situations as well. You might have seen that there are possible configurations of things that are more stable than others. Okay, even though both of them are stable. Okay, that kind of quantification will be done at a later class. But right now our objective is to figure out whether or not the impulse response is absolutely integrable, or in other terms, whether or not the system is stable. That is kind of the goal, or rather the objective here. All right, so to serve this objective, we have to use, or rather take the help of partial fraction expansions. Before we can take the help of partial fraction expansion, there is a fundamental theorem of algebra that says that if I have an nth order algebraic equation, then that has n number of algebraic solutions, n number of solutions in the complex plane. So this is, the denominator is an nth order polynomial and the numerator is a mth order polynomial. So we would have n number of solutions in the denominator and m number of solutions in the numerator. The solutions of this equation are known as the zeros, because if I put any of the value of the solutions in this, then what I get a zero in totality. Okay. Similarly, the solutions of the denominator's polynomial are known as the poles of the system, because if I put any of those values, then I get a zero in the denominator, that in turn makes this infinite. So those are called poles. So this system has m number of zeros and n number of poles. Okay, so this system has these two features, for example. All right. So with that being said, what I can do actually, now I can do some simplification on this. So I have this expression. Now tell me if this is a valid simplification. Okay, we can actually divide the numerator and the denominator. We can divide the numerator and the denominator with a to the power n. Okay, with the coefficient of the highest power. Okay, so an, I mean, we can divide the numerator and the denominator with an. That's a coefficient of the highest power. Okay, so let's do that. So what we essentially have, we can take this out of this. So I have an, and that would give us s to the power n plus something like an minus 1 by an s to the power n minus 1, and so on and so forth, plus a1 by an s to the power 1 whatever, plus a0 by an, that's a constant. All right, so we have this in the denominator, and in the numerator we can also, at the same way, we can actually divide by this factor here. Okay, but instead let's do something slightly more interesting. Okay, we can take bm, factor out bm out of the numerator. If I do a very similar thing, so we have s to the power m plus something like bm minus 1 by bm s to the power m minus 1 plus, and so on and so forth, up to b1 by bm s plus b0 by bm. So that is something we can actually write. Okay, so this bm by an, this factor, so that's a constant, right? Since all these numbers, a1, a2, a3 up to an, and b1, b2, b3 up to bn, so that's represented with ai, bi here. Okay, these are all constants. So this ratio bm by an can be considered to be a constant, and let's write that constant as k. Okay, so we have a constant k, and then of course we have the same thing. So let me just copy and paste it rather, instead of writing it once again. So instead of writing it once again, so we have a constant k. Okay, so where we are saying k is just bm by an. All right, so ratio of the highest order coefficients then. All right, so now that's a representation. That's a very simple, not a very difficult representation, right? Now we can see that we have an nth order polynomial here in the numerator, mth order polynomial in the numerator, and an nth order polynomial in the denominator. So ideally they can be factorized now in the complex domain. So if I have complex numbers in my repertoire, then this denominator actually factors out into n number of factors in the complex domain. So essentially they would look like s minus p1, s minus p2, s minus p3, and so on up to s minus pn. So these are the solutions. I'm saying that p1, p2, p3, p4 up to pn, these are the solutions of this equation. Okay, similarly I would have k times s minus z1, s minus z2, s minus z3, and so on up to s minus zm, where again I am saying that z1, z2, z3 up to zm are the solutions of the numerator's equation. In other words, these are the zeros of the equation. So Z1, Z2, Z3 up to Zm, these are the zeros of the system. Okay, zeros of the system, because if you put S equal to Z1, okay, then what happens is that this numerator becomes 0, so the entire transfer function becomes 0. Okay, any of these would make the transfer function become 0, and just like that, P1, P2, P3 up to Pn, P1, P2, P3 up to Pn are the poles of the system. So we already have this knowledge due to one previous discussion on that. All right. So this system has m number of poles and m number of zeros and n number of poles. All right. So this form of the transfer function is called the zero pole gain form, or simply known as the ZPK form. Zero pole, K stands for gain. Okay. So this is called the ZPK form. Z stands for number of zeros, and P stands for poles, and K stands for the gain. So this is called the ZPK form of the transfer function. Now there is an advantage of this kind of a formulation, because now with this formulation we can actually write this to be equal to something slightly more important. Okay. For example, we can now do a partial fraction expansion on this entire thing. We can say that this actually equals to n number of partial fractions, because that's how we do partial fractions. Okay, so we would have something like k1 divided by s minus p1. Again, remember that we are saying that these are all first order factors, and yes, if I consider this to be complex numbers, so all these can be complex numbers, by the way, then these are first order partial fractions. So this is going to be something like k by s plus p1 plus another k by s minus p2 plus k3 by s minus p3, and so on up to something like kn by s minus pn. That's going to be the representation. So here we are assuming that m is strictly less than n, because if m is equal to n, then there will be another constant term associated with that. If the order of the numerator is equal to the order of the denominator, then there has to be one constant term. We're just saying strictly less than n, then we can actually deal with the constant term later. Okay. That's how we do partial fractions. Okay. So again, all these quantities are complex numbers. So just to note that all these quantities, like all these z, all these p, all these and all these k, are all complex numbers. So they are members of the complex set. So they are all complex numbers. Okay. Obviously, remember that real numbers are just a subset of complex numbers, so not a problem there. So if you now express this in this way, there is an advantage. What is the advantage? The advantage is in figuring out the impulse response, because see, we are trying to figure out a way in which we can describe the impulse response, right? And we can figure out the absolute integrability of the impulse response. So let's calculate the impulse response. So this is GS, remember, this is GS. So what is GT? Therefore, if I say therefore, what is GT then? GT would be the inverse Laplace transform of this quantity. And obviously, what is the inverse Laplace transform of this whole quantity? The separate inverse Laplace transforms of all these quantities added together, right? So we have the inverse Laplace transform of the first quantity. So that becomes k1 e to the power p1 t. Okay, obviously times ut, and we're going to write the ut in the end. Similarly, for the next one, this is going to be k2 e to the power p2 t. For the next one, it's going to be k3 e to the power p3 t, and so on. And in the end, it's going to be kn e to the power pn t. and all this thing gets multiplied with ut, because all of them are going to have ut. All right, but since all this p1, p2, p3, they are complex numbers, right? So they have a real part and an imaginary part. They would have a real part and an imaginary part. So let's say that we assume that p is expressed that way. So it is going to be a plus j b. Okay, so that's the complex representation, obviously. So that's the real part and the imaginary part. All these p's are going to be represented like that. Okay, so they are complex numbers. So in other terms, pi is going to be ai plus jbi. So p1 is going to be a1 plus jb1, p2 is going to be a2 plus jb2, and so on and so forth. So assuming, okay, so we have gt equals k1, that's a complex number, not a problem. Then we have e to the power a1 plus jb1 times t plus k2, e to the power a2 plus jb2 times t plus k3, e to the power a3 plus jb3 times t, and so on up to kn e to the power an plus jbn t, and all of that multiplied with ut. Okay, to make sure that everything is column. All right, not a problem, I hope. All right, so now we can actually expand this. So we now have, you see, you look very carefully, these are just complex frequency terms. This a1 plus jb1, that's a complex frequency term, right? a2 plus jb2, this is a complex frequency term. a3 plus jb3, this is a complex frequency term. All these things are complex frequency terms, right? And we know how to deal with these complex frequency terms. Okay, and we actually have some intuitive idea on these complex frequency terms. Okay, so let me just show you. Let's go back to the 8th lecture that we had on this. Let me just show you a few pictures from our previous discussion there. Okay, hold on. I guess this one. No, not really. This one. Yeah. So that was our discussion on the complex frequency, which the. All right. So that was our discussion on complex frequency, and that was our eighth lecture. And there we actually had a comprehensive discussion on the complex frequency. You saw when the real part of the complex frequency was negative. Okay, real part of the complex frequency was negative. It was decaying, right? So when the real part of the complex frequency was negative, all these examples, we see the real part of the complex frequency was negative. So whenever the real part of the complex frequency was negative, it was decaying. Okay, but when the real part of the complex frequency was 0, it was neither decaying nor increasing in magnitude. But on the other hand, when the real part of the complex frequency was positive, we saw that the signal was actually increasing. Okay, it was not decaying, but it was automatically amplifying. Okay. So that would give us some information on what we sought to do in this one. Okay, so now we expand this exponentials out. So we write k1 e to the power a1t. Remember, a1 is a real quantity. Okay, times e to the power jb1t. Not a problem. Plus k2. Again, any of this could be 0, any of this could be negative, positive. It doesn't matter really. Okay. So a2t, we are writing a general case. jb2t. I'm not writing the third term. Okay. It only would make things unnecessarily complicated. kn e to the power ant times e to the power jbnt. And all of that multiplied with ut. Ut is just there to make sure that the system starts at t equal to 0, and before that everything has a value of 0. All right. So now look at this k1 e to the power a1t, and then look at this quantity. Okay, e to the power jb1t. So e to the power jb1t, that's a pure complex frequency, pure frequency term, and that is just cos b1t plus j sine b1t. So that's a general sinusoid with frequency b1, right? Same thing goes for the next one. That's going to be k2 e to the power a2t, and then I have cos b2t plus j sine b2t. Okay, and so on and so forth up to something like kn. I have kn e to the power ant, and then I have cos bnt plus j sine bnt. Obviously, everything, all of this is true when t is greater than equal to 0. Okay, so let me just write it down. Okay, instead of writing ut, let's just write it down like that. All right, so that is something we have. Okay, of course, we know that these are now pure sinusoidal terms, and they are bounded between minus 1j and plus 1j, between those two values, right? So essentially, they are circles in the complex plane. Okay, they are circles in the complex plane, unit circles in the complex plane. So they are pretty bounded. Okay, so now when we talk about the boundedness, these are always bounded. These quantities are always bounded. Okay, these terms are always bounded. So I can just simply say that these quantities like cos b1t plus j sine b1t, these quantities are always bounded because the magnitude of this is always equal to 1. Okay, because this is equal to cos square b1t plus sin square b1t, and that's equal to 1. So this is always bounded, right? These quantities are always bounded because all of these quantities are always bounded. So let me just write it down. So these, and then obviously this, or this, I mean to say this, these quantities are always bounded. So they won't affect the boundedness, right? They won't result into any. So they cannot make the integral go to infinity. Okay. All right. What can make the integral go to infinity? These terms, right? These terms can make the integral go to infinity. Okay. Make the integral go to infinity. So yesterday I gave you a problem where if you did solve the problem, you saw. So let me again reiterate what I'm saying here, that these are the terms which are responsible for converging or diverging, right? These terms are which are responsible for converging or diverging. Ideally, they should converge, right? All of them should converge. So in order for this to exist, I mean, in order for this to exist, or rather, in order for this impulse response to be absolutely integrable, finite, if this is finite, this would imply that this signal, when time is very large, actually decays, right? So this is a decay. This should be a decaying term. This should be a decaying term. This should be a decaying term. All of these terms must be decaying terms, right? So all of these terms must be decaying terms in order for this to be finite. That's obvious, right? If any of them exponentially grows instead of decaying, then the integral will result into an exponential thing, exponential growth, right? The integral will not converge. If any of them grows instead of decaying, then the integral will not converge. So having a finite value for this integral indicates that this term must decay, this term must decay, all of these terms must decay. So in other terms, that we are saying this is finite, that implies that k1 e to the power a1t, okay, must go to 0. K2 e to the power a2t also must go to 0. So on and so forth. Kn e to the power ant also must go to 0 as t tends to infinity. So when I wait long enough, all these terms must approach 0, or at least they tend to infinity 0. Otherwise cannot happen. Okay. So if they tend to infinity, there are two possibilities, right? When t tends to infinity, these terms can either go to 0 or go to infinity, right? Because they're exponentials. They can either go to infinity or become 0. So unless they become 0, then this cannot be finite, right? If any one of them, even if a single one of them goes to infinity, then the whole sum becomes infinity, right? Because infinity plus anything is still infinity, right? So all of them, every single one of them must approach 0. Okay, all of them together, all of them, every single one of them individually and together, they should approach 0. So all of them should approach 0. But when is that possible? So this is possible if all of them would approach 0 only. So this is possible only if all of these quantities like A1, A2, A3 up to AN, they are negative, right? All these quantities must be negative. So A1 must be negative so that this power actually takes it to 0, because e to the power negative infinity becomes 0 and whatever. So must be negative. So all of these quantities must be strictly negative. Okay. So all of these quantities must be strictly negative. But what are these? What are these A1, A2, A3, etc.? These are the real parts of the pole locations. So these are the real parts of the pole locations. So in other terms, I can say that the real part of the first pole, the real part of the second pole, the real part of the third pole, so on up to the real part of all of the poles, essentially real part of the nth pole, all of them must be negative. The real parts of all of the poles must be negative for stability. So this is a necessary and sufficient condition for the stability of continuous time linear time invariant systems. Okay, so if the real parts, so this is exactly the same thing, this exactly tells you the same thing. So if this is true, then the impulse response would be absolutely integrable, and if the impulse response is absolutely integrable, then the system is stable. Okay, all right. Now let's get back to the previous question, the question that I gave you in the last class. Okay, questions that that we discussed in the last class. All right, so let's get to that. Yeah, let's think about this system. Let me again switch the view here. All right, so this is a system that we talked about in the last class. So you calculated the impulse response and you saw the impulse response divergence, right? So let's talk about this. Okay, let's talk about this. So we see that let's see the same examples. Okay, the transfer function was 2 divided by, what was it? Was s minus 3. All right, 2 divided by s minus 3. All right, 2 divided by s minus 3. Question is, how many zeros and how many poles does the system have? This has no zeros. Okay, the numerator polynomial is 0th order polynomial, and it has one pole, right? One pole. So how many zeros? No zeros. And how many poles? Only one pole. And what is the pole location? That's just P1, and P1 is essentially 3, right? You see that's just 3, and since this is 3, obviously this is like 3 plus 0j. Okay, this is a complex number. What about the real part? The real part is positive, which indicates that I have one pole that takes this to infinity. So I have one pole that takes one of the quantities to infinity, one of the factors to infinity, and thus the impulse response will not converge. Okay, and therefore, since this is positive, that implies therefore unstable system. All right, another example that we discussed in the last class was 2s plus 3 gs, 2s plus 3 s plus 2 times s plus 5. Now it has 1 0 and 2 poles in this system. Okay, it has 1 0 and 2 poles. Now what are the pole locations? Pole locations are at -2, so this is like -2 plus 0z, and another pole location is at -5 plus 0z. Okay, so it's like -2 and -5. If we put just -2 and -5, the denominator will become 0. Those are the poles, right? And look at both of them. For both of them, the real part of the pole location are negative. So all of them, rather, this is the condition, all of them must have negative real parts, right? Must have negative real parts. And since all of them have negative real parts, then we say that the system is stable. So both of them have negative real part. Both of the poles have negative real parts. So both of them are negative. So stable system. Therefore, stable system. You see, it is that easy. Okay. The last example, that is something was given as an exercise to you, and the example was 1 by s minus 1 s plus 2. You see, it has zero number, so no zeros, and 2 poles. But what are the pole locations? The first pole location is at +1, so +1 plus 0j, and the other pole location is at -2 plus 0j, something like that. So you see that one of them has a positive real part and the other one has a negative real part. But since one of them has a positive real part, this condition is violated. This condition states that every component of that must be converging, right? Because see, all of these components must converge, right? If any one of them goes to infinity, the whole thing goes to infinity. Okay, if any one of them goes to infinity, the whole thing goes to infinity, and that's how the system becomes unstable. So the impulse response does no longer stay absolutely integrable, right? So if one of them is positive, so this is positive, and the moment one of them is positive, the total system is unstable. And this is something people figured out while discussing the stability of systems. So this is quite path-breaking. You see, so the whole perspective of this, because this control system engineering was developed largely in mid-1950, early 1950s and 1940s, right? Back in the day, people did not have calculators. We did not have computers. So people had to invent, scientists and engineers had to invent techniques to simplify the calculations, to reduce the amount of calculations required to analyze things. So this is one of those approaches, right? So by looking at the system without actually calculating the impulse response, we can calculate the impulse response and checking whether the impulse response was absolutely integrable or not. We can actually look at the system itself, okay, the transfer function itself, and we don't have to do any inverse Laplace transform, any calculation on that. Okay, just by looking at the locations of the poles, we can determine whether or not a system is stable or unstable. Okay, so you are asking what is necessary and what is sufficient, necessary condition and sufficient condition. This is a discussion for mathematical logic. So give me 10 minutes, I can actually discuss that, or maybe in the very next class we are going to talk about necessary and sufficient conditions. Okay. What do you want? Do you want me to discuss necessary and sufficient conditions? Because we are going to explain that. I have to explain what necessary means and what sufficient means. Okay. Okay. Just to give you a very small example. Very small example here. Okay. I can explain this mathematically, but the problem is if I explain this mathematically, then it would become difficult for you to understand. I guess rather. Okay, so let me explain this in a very slightly different way. Okay, so let's talk about mathematical statements. So you are saying that if it rains, that's a very good example. I mean, if it rains, okay, I won't go to college. Okay, so if it rains, then I won't go to college. So that's your statement. So mathematically speaking, I would call this statement P, and I won't go to college, that would actually be a mathematical statement Q. So I would say P would imply Q. Okay. So which means that if it rains, so raining implies that you won't go to college, right? Raining implies that you want to go to college. So something like that. Not a problem, right? If it rains, you won't go to college. So that's an implication symbol. Okay. Not a problem. So I, as a teacher, I went to the college and I saw you were absent that day. Okay. You were absent that day. So please tell me, can I now say that there was a rain that day? You understand the statement very carefully. So you said, if it rains, I won't go to the college. So right now it is raining, and if I go to the college, I won't see you. Just imagine the situation like that. Because it rained, right? It rained, so you did not go to the college. Fine. Now, one day I went to the college. One day I went to the college, and I see that you were absent. Okay. Can I assume that it rained? I don't understand. Can I assume that it rained? The answer is no. I cannot assume it rained. It could be because it rained. It could be because it rained. So rain could be one of the factors. But there could be another reason. Maybe you suffered from fever. Maybe you just didn't want to come to the college on that day. Didn't feel like coming to the college. Could be any reason, right? Okay. So here, if it rains, this statement P, is a sufficient condition for Q to happen. Okay. So in order for Q to happen, P is sufficient. So if it rains, then it is sufficient for you to not go to the college. So P is a sufficient condition for Q. Okay. So P is a sufficient condition for Q. If it rains, you definitely won't go to the college. Okay. P is a sufficient condition for Q, but P is not necessary for Q. Try to understand. But P is not necessary for Q. Okay. Which means that if it rains, then definitely you won't go to the college. But if you are not found in the college, then it is not necessary that it rained, isn't it? Again, let me explain. P is sufficient for Q, but P is not necessary for Q. Okay. What it means is that if it rains, then you definitely won't go to the college. Okay. So raining is sufficient for you to make a decision that you won't go to the college. You will not go to the college. Okay. But if I go one day to the college and I don't see you, so you did not come to the college, it is not necessary for me to assume that it actually rained, and that is why you did not come, right? So P is not a necessary condition. P is a sufficient condition. Okay. That's how necessary and sufficient conditions are. Okay. So this is a sufficient condition. So this is a sufficient condition. P is a sufficient condition for Q to happen. Okay. I'm going to explain what necessary condition, etc. means. Okay. For those who have some mathematical understanding, the mathematical statement says here, P is a sufficient condition for Q, and Q is a necessary condition for P. Okay. Let me just write it down. Maybe I would explain that later. I think you got the understanding what a sufficient condition means. So here, P is a sufficient for Q, and Q is necessary for P. Okay, just keep this in mind, and I'm going to explain that in a future class. I mean that very next class. Okay, because in the very next class we are going to discuss something that has these terms. Okay, you understood what sufficient condition means, right? All right. All right. So now let's talk about another system. Let me give you another system. So exercise problem. Check the stability of the system given by. So let me just give you a few transfer functions. Okay, one. So let's say this is or maybe not. Maybe just make it simple, I guess. Okay, so this system has two zeros and four poles, right? Two zeros. I'm not interested about them, and it has four poles. So what are the pole locations? Pole locations are, hold on, P1, oh, I've read just P. Okay, so the pole locations, what are the pole locations? One is -6, one is -2, the other is -1, and there are actually two -1s because this is like -1 times s minus 1, sorry, s plus 1 times s plus 1. So all of them are positive. All positive, sorry, all negative. All negative real parts, right? So stable system. All right. Question number 2. Please tell me what is the number of poles and number of zeros? Yes. So you know that's 1 0 and there are two poles. But what are the pole locations? What are the pole locations here? In order to calculate the pole locations, you have to solve this equation, right? The denominator is polynomial. So that's equal to 0, and obviously it's a second order polynomial. So s is going to be minus b plus minus root over b square minus 4ac. So b square minus 4ac, so b square is 4 minus 4ac. So that's gonna be 12 by 2a. So that's gonna be 2. So that's your quadratic formula, right? And this is becoming -2 plus minus, so that's a complex number j, root over 8. So root over 8 is 2 root 2, 2 root 2 and divided by 2. That's going to be -2 plus minus j root 2, sorry, -1 plus minus j root 2, -1 plus minus j root 2. So we have two poles, and the pole locations are at -1 plus j root 2 and -1 minus j root 2, and both of them have negative real parts. So both of them have negative real parts. So stable. Not a problem. All right. Another question. Okay. Another question now. So you see, you don't have to again check at the zeros. Really, you don't have to calculate the zeros or whatever. You can say. What's this? Yeah. All right. So what about the stability of this one? Again, you have to check the poles and zeros. Obviously, I have two zeros. Does not matter. And I have 4 poles. But just one thing to again note, I told you already, the order of the system is equal to the number of poles. So this is the third order system. This is the second order system. This is the fourth order system. So order of the system is equal to the number of poles. That's how we define it, right? So order of the system is equal to number of poles. Just keep that in mind. All right. So here we have to again solve this. So s cube, in order to calculate the poles. So s cube plus sa square plus s plus 1 equal to 0. So if we try to solve this, we get sa square factored out. So s plus 1 and plus s plus 1, that's equal to 0. So what we see is that I have s plus 1 and then s square plus, sorry, I mean it has to be 1. S square plus 1 equal to 0. So the solutions are s equal to minus 1 is one solution, and s equal to plus minus 0 plus minus 0 plus minus 1g. So the, sorry, not 4 poles, I mean 3 poles. Okay. So the pole locations are minus 1 and 0 plus minus 1, sorry, plus 1j. Yeah, 0 plus 1j and 0 minus 1j. You now have a problem. I mean, of course, one of them is negative. That is not a problem. So this is the negative. And 0 is neither negative nor positive, right? 0 is neither negative nor positive. So we don't really know. If it's positive, if any one of them is positive, then the system is unstable. If any one of them is positive, the system is unstable. Now they are neither negative nor positive. They are somewhere in between. So they are in the verge of stability and instability, or rather instability. What I'm saying, stability and instability, right? But you saw, so these are again all complex frequencies, right? But you saw what happens when I have 0 real part in the complex frequency. Okay, you saw what happens when I have 0 real part in the complex frequency. So let me get that PDF once again, what we discussed in the our 8th lecture, where we discussed complex frequency, and this is precisely why I taught you complex frequency. Okay, you saw here, let me just take a switch it. Yeah. So you saw when I have 0 sigma, okay, here we have 0 sigma, right? So when I have 0 sigma, you see, for example, this one, okay, when the these are all complex frequencies, right? I believe you remember what we used to discuss in that time. So when I have a negative part, negative real part in the complex frequency, it was decay, right? The signal was decaying. But when I have 0 real part in the complex frequency, then it was actually oscillating without any decay. Okay. Similarly, if you have positive quantity here, then it was actually increasing. But if we have 0, it indicated that it was oscillatory, right? So oscillatory means it is neither increasing nor decaying. So that absolute, so that integral, okay, would conditionally converge, will be in the verge of convergence, but not quite. It is like something like that. So okay, so that absolute integrability condition is very lightly violated. Okay, if I want to butcher mathematics here, okay, in a sense, okay, so it is not going to diverge completely, but it is not going to converge either. Okay, because the area is going to fluctuate, keep on fluctuating. So as you see, think about this blue sinusoid here. If you keep on calculating the area is never going to turn out to be or rather converge, right? It will keep on increasing and decreasing, but it will have some bounds, right? It will have some bounds. But if you calculate the area for this orange one, it will eventually be a finite value, right? But if you keep on calculating the area under this blue curve, it is going to increase, decrease, keep on doing that. It is not going to go to infinity, neither it is going to come down to 0. So it neither converges nor diverges in a sense. Okay, and that's why this is called a marginal stability condition. These are poles that are at 0. So this is neither positive nor negative. So 0, right? Neither positive nor negative. Neither positive nor negative. So this results into something called marginal stability. So we say marginally stable. Okay. So this system is marginally stable. Let me give you another example. Okay, let's take the same thing and slightly manipulate this. Question number 5. Okay, maybe get rid of this, doesn't matter. And let's multiply this with something like s minus 1. So now I have 0 zeros and 4 poles. And what are the pole locations? We just figured out 3 of them because we have to now solve this equation. Obviously, you know that. So we now have 4 poles. So poles are at -1 plus 0j. So that was this part here. And then we have 2 more, like 0 plus j1, rather 1j, whatever you want to call it, 1j, 0 minus 1j, and then we have another pole at 1. Yeah. So your question, so you asked a question, and that we just answered here. Okay. All right. So something like this. So now you see, this is good. This is neither good nor bad, but this is bad. Okay. So essentially, the term for this actually converges. The terms for these neither converges nor diverges. So not a problem. But the term for this diverges. Okay, so while integrating this, one of you are asking a question on equilibrium. To answer your question, these have nothing got to do with equilibriums, okay? Because we are not talking about asymptotic stability. Okay, we are talking about the stability of the whole system. Okay, so one of the terms are actually going to go to infinity. So we have now 4 terms in the integral, right? Absolute integral here. One term that converges, so this term actually converges. 2 terms that neither converge nor diverge, so not problematic. But we have one term because of which that term actually goes to infinity. So we have some finite quantity plus some finite quantity plus infinity, so the whole thing goes to infinity. So the moment there is even a single pole that has positive real part, the whole thing is unstable. No other thing is possible. So this is negative, this is positive. The positive real part, right? And so it is unstable. The moment one of them has a positive real part, one of the poles has positive real part, the system is unstable. Because the thing is not going to converge anymore. Because one of them goes to infinity. Does not matter on what these other values are, right? If one of them goes to infinity, the sum goes to infinity. End of story. The whole thing will diverge. All right. Now let me end today's discussion with a very simple question. Or rather, let me before ending the question, let me ask you another simple question. Say, I ask you, I give you this system. Whatever. The numerator does not matter. Let's just write a numerator polynomial. Okay, it's a function of whatever, function of s. Okay. And in the denominator, say I have something like this. Okay, please tell me whether this system is stable or unstable. Please tell me whether or not this system is stable. So now you see that you cannot tell me whether the system is stable or unstable because you have 2 options. You either calculate the inverse Laplace transform, so you get the impulse response, and from that you calculate, check whether or not the impulse response is summable, absolutely integrable. I mean, you cannot possibly invert this, right? You cannot take the inverse Laplace transform yet, unless I don't know, unless you are a living computer, maybe. You cannot calculate the inverse Laplace transform. The other option, calculating the pole locations. But in order to calculate the pole locations, which is much easier to do than calculating the inverse Laplace transform, you need to solve this equation. Thing is, how do you even solve this equation? People needed this sort of equations being solved back in 1940s, 1930s, while designing controllers for aeroplanes. Right? They needed this sort of equations. So dynamics of aeroplanes, they involved differential equations of 10th order, 11th order, okay, very frequently. I mean, how do you even solve such a differential equation? I mean, solve this polynomial. Unbelievable, right? You cannot solve this. Of course, you had numerical methods like Newton-Raphson method. So imagine solving this equation, finding all 7 complex roots using Newton-Raphson method by hand. You don't have calculator even. You don't have to do every calculation. It will be a really, really long process. It will take you days. And then there will be every possibility that you would make a mistake. That there will be every possibility that you would actually make a mistake. Right? So what people obviously did, the engineers back then invented a method. Really try to understand one important thing. Do we really need to calculate the exact pole locations, or do we need to actually solve these equations? Do we need to solve these equations? The answer is actually no. All we need to know is whether or not all the poles have negative real parts. All we need to know are whether or not all the poles have negative real parts. Okay? We don't actually need to calculate the solutions. That is something people figured out back in the day. Now, obviously, the obvious result was they invented a technique. Back in the day, they invented a technique, like in 1940s, people invented a technique in which you actually don't have to solve this equation. You don't have to solve this equation, but doing some manipulation on this, without actually solving this equation, you would be able to definitively tell how many poles have negative real parts, how many poles have 0 real parts, how many poles have positive real parts. Okay, so that is the technique people invented back in the day, and that is exactly what we are going to study next. So the next thing that we are going to study is going to be how to actually know about the solutions, how to actually know how many poles have negative real parts, how many poles have positive real parts, how many poles have 0 real parts. Okay, just by not solving this, without solving this, by doing some simple calculations. How can we even think about that? That is the technique we are going to learn next. So again, the entirety of this subject is based around simplifying our life, simplifying the calculations, getting the same insight out of a discussion, out of a system, but without actually doing much of any calculation, without doing many complicated calculations. So that is something we are going to study next. Just before we leave though, this is the complex plane. So complex plane is essentially a 2D coordinate plane, right? So not a problem once again. So this is the real axis and this is the imaginary axis. And since complex numbers are represented as S, complex frequency essentially, it is often called the S plane. Okay. And so if we have poles or zeros for a system, we can actually plot them. Okay. We can actually plot them. Essentially, say I have a system that has certain poles at certain locations. Of course, this is a coordinate plane, right? This is S, and so this is sigma, this is j omega, right? We can actually plot them. Okay, so I can have certain poles in these locations. These cross symbols are used for denoting poles. Okay, I can have a pole somewhere here. Maybe I have a pole somewhere here. Just example. This is just an example. Okay, and I might have certain zeros. Okay, say I have a 0 here, maybe. Okay, 0 that written as O, like that, and I have pair of zeros here. Obviously, you know that complex solutions will always appear in pairs. So if the result is complex, then they will appear in pairs. So conjugate pair. So this kind of plot is known as the pole zero map. It's a pole zero map. So this visually depicts the locations of the poles and the zeros in the complex plane. Okay. So these are the locations of the poles and the locations of the zeros. Now this kind of pictures are useful for the fact that by looking at this picture, now you can actually talk about the stability. Because you can see, we're not interested about the zeros once again. Looking at the poles, you can see that all of the poles have negative real part because this is the real axis. And all of the poles have negative real parts, right? This is the origin, and on the left of this have negative real values, right? Alright, so all of the poles here depicted here have negative real parts. That's how, if the pole zero map for a system looks like this, we can say that the system is stable. If the pole zero map looks something different, we might infer otherwise. Okay, so these are the pole locations. Let me just instead give you some markers rather. So this denotes poles, and this would denote zeros. Okay, all right, so that's fine. So this is called the S plane. Okay, it's called the S plane, and that's a simple discussion, I hope. Okay, so just to tell you the other way in which this statement is stated, that we said that for stability, the poles must have negative real parts. Okay, must have negative real parts. So the poles must lie to the left of this imaginary axis, to this vertical axis. So anything that is to the left of this vertical axis have negative real values, right? Negative x component, rather negative real component. So in other terms, people often say that the poles must lie on the left half plane for stability. So the poles must lie on the left half plane, left to the left of the imaginary axis. So this half plane, so the left of the imaginary axis is known as the left half plane. So this is the left half plane, and this is the right half plane. Okay, so this is the right half, and this is the left half. Okay, so if all the poles are on the left half plane, then we say the system is stable, and this is again the necessary and sufficient conditions. Okay, so that is, let me just write it down here maybe. So I'm saying that all the poles must lie on the LHP, left half plane, for stability. If any of them is somewhere else, then the system is no longer stable. So let me give you a few pole zero maps and ask you whether or not the system is stable, and you would tell me whether or not the systems are stable in the discussion. Let me draw a few axes here. Now I'm not giving you the transfer functions. Okay, so this is sigma, this is the j omega. Obviously this is the S plane, I'm not writing that. All right, and the same zeros do not matter again in terms of stability. Let's say this system does not have any zero, or maybe, oh no, maybe just write it down there. Okay, so picture number one. Is this system stable or unstable? So please tell me in your answers here. Picture number 1, 2, 3, and so this is my picture number 1, picture number 2, picture number 3, and picture number 4. Tell me which one of these is stable, which one of these is unstable. Those are the pole zero maps for the system. I don't have to. We were saying the first one is stable. The answer is no, wrong. The first one is unstable. This is unstable. And why is it unstable? Which one is the culprit? This is the culprit. This is the culprit for which this is unstable. This is the culprit for which this is unstable. This is the culprit for which this is unstable, right? Because there is one pole which is on the right hand plane. The second one is marginally stable, and it is because of these. The second one is marginally stable. It is because of these. Okay. The second one is marginally stable. Okay. This one is absolute stable, no problem. This one is stable. And what about this one? What about this one? The last one? Yes. So the last one is unstable, right? And these are the culprits, obviously. These are the culprits for which the system is unstable. And there is one last one I want to discuss. So most of you have got the answer correct. Answers correct. So that's quite fascinating, I would say. Okay. And what about this one? Is it stable or unstable? Or marginally stable? Obviously, this is unstable. Even though there are poles on the, there are poles here to make it, trying to make it marginally stable, but no, this is the actual culprit which is making the system unstable. All right, this is unstable. So this is a very good way. No, it is not marginally. It is unstable. It is not marginally stable because these two, for these two, the terms will oscillate. Okay, the integration will not converge. But for this term, for the term associated with this, the integration will diverge. Okay, so one term will go to infinity in the integration. So integration is essentially sum of few terms, right? In that. So if one of the terms goes to infinity, the whole thing goes to infinity. Okay, these are oscillatory terms, but that won't matter because this actually goes to infinity. The term here associated with this actually goes to infinity. That e to the power term here, right? So the impulse response will not converge, and that's how the system is unstable. All right, so I guess you can actually look at pole zero maps. These are again called pole zero maps. Okay, and you can see that you can actually talk about stability very easily by looking at the pole zero map. But sometimes constructing this pole zero map is a bit difficult. Okay, given this kind of problems, if you face this kind of problems, then constructing the pole zero map by itself is a difficult task, and that is something we're going to solve in our next class. All right. So thank you very much for being here for so long, and I will see you next week. Any question? I will just wait for 2 more minutes here. If you have any questions, you can ask at this point. All right. So I'm waiting here. If you have any question, feel free to ask. Okay, yeah, one of you asking about the rationality of transfer functions. This is something we have to discuss later on. For the moment, assume that the power of order of the numerator is always lower than the order of the denominator. At most equal. At most equal. So the rationality term we are going to explain later on. Why the transfer function is to be rational transfer functions. Anyway, that's a future discussion we're going to have. But definitely, you can stay assured that we're going to discuss that. Anything else? Any other question? No. Very good question. Are there something called marginally unstable? No. Because marginally stable, what do you mean by marginally stable? This is again a bad term. Okay, Shantanu has got a very important question. I'm going to explain that before I explain what marginally unstable could mean. Okay, so what we call marginally stable is the condition under which the system is neither stable nor unstable. Okay, the system is neither stable nor unstable. That's how it's called marginally stable, because it is not, strictly speaking, unstable. Okay, it is not going to infinity. Strictly speaking, it is not diverging. Okay, so that's why we call it marginally stable, and there is no marginal instability. Okay, the system can be either stable or unstable or marginally stable, which is neither stable nor unstable. Okay, on the verge of instability. Okay, that's the name here. So there is no marginally unstable thing. Okay, so which means it's a very close to instability. Marginally stable means it is almost stable or almost unstable. It's not like that. It is neither stable nor unstable. It's marginal. Okay, in the very margin, and quite literally it's in the margin, right? For example, the systems that are marginally stable have poles on the margin, right? Neither on the left half plane nor on the right half plane. So they are marginally stable. Okay. And one of you are asking the rationality of transfer functions. Does it play any important role in no? Okay, there is another question. I'm going to explain that shortly, don't worry. So does it play, one of the question is that does it play any part in the stability? Actually, yes and no. Okay, it plays another important part, and to explain, I could just explain it right now, but that would actually kind of feel like it came out of nowhere. If I have a transfer function that is non-rational, has a order higher in the numerator than the order in the denominator, that actually creates a non-causal system. Okay, that actually creates a non-causal system, which is not possible for continuous time systems. For continuous time systems, it is not possible to create a non-causal system. And later on, we are going to prove that having a higher order in the numerator creates a non-causal system. So that would create a problem. That would create a reality-breaking problem, really. So we don't have systems like that. We cannot create systems. I mean, technically speaking, we can create systems like that, but highly not recommended. Okay, using op-amps, you can create a differentiator, and the differentiator ideally would have a transfer function like S divided by 1. It has 1, 0, and no pole. So technically, it has an order. The numerator's order is higher than the denominator's order. Okay, but it has so much problems. So that's why a differentiator can never be used just like that. A differentiator is always used with a role of pole. Yeah, these are the things we are going to discuss in future. Okay, so that is something to keep in mind. Okay, and one important question is, someone is saying marginal stability might mean conditional convergence. No, it's not conditional. It is marginal stability means it is neither converging nor diverging. Okay, it is oscillating. The value of the integral is oscillating. Okay, it is within a certain bound. Okay, but it is not going to go beyond that. It is not going to converge to a fixed value. It is going to keep on changing, right? It is going to keep on changing. A very simple example could be something like this. What is this integration? 0 to infinity on sine t dt. Can I say this goes to infinity? No, I cannot say this goes to infinity. Because if I draw this, you would see that the area becomes first positive, then this cancels out the area and immediately becomes 0. And then the area once again becomes positive, and then this part cancels out the area and becomes 0. So you can see the area fluctuates, right? So this integration does not go to infinity. So I cannot say it goes to infinity. Okay, it does not go to infinity. But neither does it go to a fixed value. So this is not a fixed value. I cannot just say this is equal to a value A. Okay, so I cannot say this goes to a fixed value, but also I cannot say this goes to infinity. So this neither diverges nor converges. So this keeps on oscillating. That is what marginal stability actually intends to mean. But you might have gotten one point by just guessing there is something called conditional stability, which I'm going to discuss later. Conditional stability deals with conditions that we can impose on a system to make it stable. Yeah, oscillating functions neither converge nor diverge. All right, so that is the overall discussion here. We're going to elaborate on this. Of course, in the next class, we're going to learn quite a bit. And important thing is that we are going to discuss a technique that would allow us to actually find out how many poles out of this are on the left half plane, how many poles are on the right half plane, how many are on the j omega axis, without actually solving this equation. But of course, nowadays we can solve this equation. We have Python and we can just use a very simple Python function. Let me just show you that just for the kicks here. Let me show you how we can actually solve this complicated equation pretty easily. Python. Let me just start up Python. Okay, and just hold on. Let me bring this to another page. Okay, and hold on 1 second. All right, so that's Python. All right, so we can actually use the NumPy and say roots and ask it to solve the polynomial for us, and it's a very easy thing to do using NumPy. Okay, so I can ask it to solve the polynomial for us. It's a very easy thing. Since we have computers, but back in the day, like 70 years ago, we did not have computers. Like 70, 80 years ago, 70, 80, 90 years ago, people actually used aeroplanes, made aeroplanes, fighter aircrafts. They had to solve so many complicated equations. They did not have computers, so people had to invent techniques. So what was the polynomial? Let me just save this file first. All right. So, all right. So we are going to solve. So this is one. So just at the coefficients 1593, 1593, 122, 1593, 122, and then 3700. 3700. Okay. So I'm just asking it to calculate, show me the roots, and it will show me the roots. And those are the, so not, yeah, so, yeah. So that, these are the coefficient. That's how you call the function from NumPy. And it is giving me the roots. You see, this is one root. So it has a negative real part. You see, these are the negative real part. Okay. So that's the real part, negative real part. The conjugate pair, it has negative real part, no problem. So also negative real part. Now we have one positive real part, another positive real part. So we have two poles which have positive real parts. Okay, that's how this system is going to be unstable. That's how this system is going to be unstable. We have two poles that have positive real part. But using this simple Python function, actually, you can easily calculate the roots. Okay. But back in the day, this wasn't available. Right? We had to do manual calculation. All right. So that is the technique we are going to actually learn in the next one. So anyway, so if you have any query, ask maybe, or otherwise we're going to end the discussion at this point. Once again, thanks a lot for being here and listening to me patiently. All right. Okay, I just got a question I don't understand. You're saying how could it recognize how much constant value is present in the polynomial? I don't understand what you're saying. How could what recognize what? Can you please explain your question? As I said, can you please explain your question? I know maybe it's getting delayed by your side. Okay, you're saying by using Python. Yeah, it is automatically going to take the last one as constant. So yes, that's the answer. So the coefficients here are just like 1. So technically this is just a, so using numpy, you can actually say np dot roots, and you are going to write 1, 5, 9, 3, 1, 22, 37, 100. So last one is going to be the coefficient of the 0th power. So last one is going to be the coefficient of the 0th power, and that's how it's going to be treated as a constant. 0 power, 1 power, so this is the 0 power, 1 power, 2, 3, 4, 5, 6, power 7. Okay, that's how it is treated. Okay, so that is, I think, easy to understand. So you just write down the coefficients one after another, and that actually gives you the solution. All right, so thank you very much. I will see you next week.